Now here we've got a circuit which is nearly 200 years old, and more amazingly than that, it's still used in electronic circuits today, particularly with temperature sensors. And that circuit is called a Wheatstone bridge. What does it mean? We've got a potential divider on this side. It looks more complicated because I've got an option of 2 resistors here at the top selected by this switch and 2 resistors at the bottom selected by this switch. And we've got exactly the same on the right hand side of the board. So 2 potential dividers. But the really clever bit is this meter in the middle, which is a voltmeter showing us the difference in voltage between these 2 points in the circuit. The point between R1 and R2 and the point between R3 and R4. Let's fire up the board. Now we've got 3 digital voltmeters shown here. The one at the top here is the supply voltage that we're getting from these batteries. So it's just a touch under 5 volts. This red meter here is showing us the voltage between R1 and R2 to ground. So it's giving us what the voltage is between ground and that point. And this one is showing us the voltage from ground to the point between R3 and R4. And you can see they're reading different voltages, and that difference is shown in the panel meter in the middle. Now let's look at this left-hand side first. At the moment, these switches are to the left, so the resistors we're using are these 2, and they're both the same value. Happens to be 200 ohms, but to be honest, that's pretty irrelevant. So what's happening is the voltage is being split evenly between these 2. And that's why that voltage there is almost exactly half the supply voltage. Now this is a real working examples with resistors with tolerances and meters with tolerances, so it'll never be absolutely spot on, but it's pretty close. So with the same value resistors, we're getting half the voltage. Now on this side, we've got a 75 ohm resistor and a 150 ohm because these switches are again switched to the left. If we take the total resistance of these 2, which is 225, we've got 2/3 across the bottom and 1/3 across the top. Now that means that this voltage will be 2/3 the total. Again, these are real working examples, so these values might not add up exactly, but it's going to be pretty close. So what we've got on this side is a ratio of 1 to 1. On this side, we've got a ratio of 1 to 2, because that's double that one there. Now, if I switch this across to here, we're going through that 150 and that 150. So these 2 values are the same. So we've now got a ratio of 1 to 1. This meter here is showing half the supply voltage. And the meter in the middle is showing 0, because if we look, we've got no real difference now between the voltages on the sides. This side we're using 200 ohm resistors, this side we're using 150, but it doesn't matter. The current will be different going through the sides, but the voltage on the centre points is going to be the same. If I move across to here, we've now got a 3 to 1. We've got 75, 25. And if I move to 33.3 ohms and 100 ohms, then I've got a 3 to 1 ratio on this side. So you'll notice that the voltage on these 2 meters again is almost exactly the same, and the center meter is reading 0 again. The important thing here is that the meter will always read 0 if the resistance ratio on one side of the board is the same as the resistance ratio on the other side of the board. And that's the takeaway that we've got for the next board. When the bridge is balanced, 0, R1 divided by R2 equals R3 divided by R4. Now this may look very different from the previous board, but we've still got a Wheatstone bridge here. Let's have a look. We've got a supply from these 2 batteries, which actually are in parallel, and it comes across the top here, and then with this selector switch we can select which of these mystery resistors that we are going to use for R1. And it comes down here, and we've got a switch here where we can choose which of these 2 resistors we're using for R2. This time we've got a digital meter in the middle, and we come across to the right hand side where we've got a variable resistor going from supply to ground, and that variable resistor is here. What we've got is a very, very thin piece of nichrome wire which has a resistance of almost exactly 1 ohm per centimetre. So we've got 40 centimetres, it goes across here, through this and then back here. So in total that's a 40 ohm resistor. So let's switch the circuit on. At the moment this is showing 0 because the centre point isn't connected. But if I put it onto this wire here, it will show a voltage. And if I slide it along, we can see the voltage changing in the meter. Now if I move it across till I get 0, if I move it the other way, then it's going to a negative voltage. And what I'm doing is I'm moving it up and down to get to the point where there is no voltage between that point in the circuit and this point in the circuit. Now what that means is that the ratio of resistance on the left side of the board is the same as the ratio of resistance on the right side of the board. With all these markings that I've laid out, I've got here ×2, and what that means is the resistance at the top is double the resistance at the bottom. So R3 is now twice the value of R4, and that means that this mystery resistor is going to be twice the value of R2. So at the moment R2 is 10 ohms, so our mystery resistor under here is going to be 20, and if I move the slider over we can see there that it's 20 ohms. This circuit was used before multimeters were around to establish the resistance of unknown resistors, because if we knew 3 of the resistor values we could work out the 4th. Now if you've got the board in front of you, have a go at moving the end of the lead up and down the wire until we get a 0 point, and then use the maths that we've got on the board to work out what the resistor is. Sometimes you'll want to have the switch to the left so it's pointing to 10 ohms, and other times to the right so it's on 100 ohms. If you haven't got the board in front of you, I'll now go through these other 4 to give you an idea of what's going on. This all sounds a bit crazy and a bit complicated, but when it's in your head, it's a really useful piece of understanding. So we'll switch to the second option now. So we're going to work out what the resistor is under this one here. And I'll put the end of the lead on here, and that's, oh look, it's getting smaller. I really can't remember what the value is here. Right, that's 0 there. If I swing it to the left, you can see it's going negative. So what this is saying is that the value at the top is 6 times bigger than the value at the bottom. So R3 is now 6 times bigger than R1. So with that across that, R1 is 10. So we're saying that it's about 60 ohms. If we move it across, it's 56, which with what we've got here is really pretty close. So let's move on to the third one, and which we'll have a look. Oh, it's quite a high voltage. It's going down, going down, going down, going down. And then when we get to here, we come back up, and it's going to be 0 there. 0 there. So that is saying that the value of R1, so that's going to be between 1/2 and 1/3 of 10 ohms. That's probably going to be sort of about 6 ohms or so. If we move it across, it says it's 5. So we'd have expected it to have been about there, but it's a little bit out again, just because we've got tolerances here. Let's move on to the next one, which is, we're having a look. Oh, we've got, oh, hang on, no. We must make sure we're on that. Right, so it's quite a high negative. So if I move right up, no, I'm going the wrong way, going the wrong way. Right, now if it's very, very close to the end, then it probably means that we're better off with the other resistor. I've got it here, but it's very close. So let's switch that to 100. And, oh look, it's about there. So we've got this. So this is saying that R1 is 100 times about 3 1/3. So 3 1/3 times 100 is 330. And if we move that across, oh, that's exactly 330. I've balanced the bridge, and it means that I know the ratios, and knowing the value of R2, I can get the value of R1. Let's try the last one. We've got minus, no, it's getting bigger, so let's keep going. It's going down, 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 down. Right, oh, move it along. Oh, right. So that's over the times 2. So that's implying that R1 is 100 times 2, which is 200. And there we are. So this is how the Wheatstone bridge works. We've got a variable resistor to try and work out what the ratio of resistance is, and knowing that and what the value of the resistor is here at the bottom, we can work out the fourth one. Now, I know with multimeters it's much easier these days, but the idea of this circuit is, as I said before, still used today.